In this video, we're discussing power series. This is our introduction to power series. I will define a power series for you. We'll talk about the center of a power series. We'll define the term coefficient of a power series. We will look at a couple of geometric power series, and we'll discuss the partial sums of a power series and what they represent. And then finally, we'll talk about the interval and radius of convergence of power series and their various forms. Okay, so a power series is a special type of infinite series. You've been dealing with infinite series. This is just an infinite series that is the sum of powers of x. It looks like an infinitely long polynomial. So a polynomial with infinitely many terms. It's not what it is exactly, but its partial sums are polynomials. So here's the form of a power series. A sub n, that's a constant. It depends on what n is. For a particular n, it's a particular constant. But we just have a constant there. And then it's multiplied by x minus a constant c to the n. Now x is a variable, c is a constant, a sub n is a constant for a particular n. And n is changing. N is 0, then it's 1, then it's 2, and it's increasing the whole time. So even though it doesn't look like it looks like you've got a lot of variables here. There's really only one variable, and the variable is x. So we can think of this as defining a function of x. It's a function of x that only converges sometimes. It'll converge for some values of x. And we'll see that in a little bit. But let's just expand this to get a better sense of what's going on. When I substitute in n equals 0, so I'm replacing all of my n's with 0. I get a sub 0 times x minus c to the 0. And x minus c to the 0 is 1. So we get a sub 0. And then I substitute in n equals 1. We have a sub 1. It's the n equals 1 term. And we're multiplying by x minus c. I'm replacing n with 1 to the first. So that's just a sub 1 times x minus c. When n equals 2, we get a sub 2 times x minus c squared. You see that n is the only thing that's changing. The next one, I think if you see the pattern, you'll know what it is. When n is 3, I'll have a sub 3 times x minus c cubed. And the pattern continues. So we've got a sub 2 times x minus c squared plus a sub 3 times x minus c cubed, and so on. It goes on forever. That's a power series. Now these a's are constants. Generally that's a formula involving n. You're going to substitute in the values of n and you're going to get these constants out front. Those constants are called the coefficients of the power series. So a sub 0, a sub 1, a sub 2, all the way through a sub n, and you continue. Those are coefficients. And this number c that we're subtracting from x, that's called the center of the power series. And that term center is going to make more sense whenever we look at the partial sums of these guys. But using the notation in our book, the a sub 0, a sub 1, a sub n. All of those are just numbers out front. Those are the coefficients of the series. And c stands for center. We're subtracting the center from all of those x values. So here's an example. Let's say I give you this series. I have this sum as n goes from 0 to infinity of x over 2 to the nth. Now this represents a function. If you give me a particular x value, I'll plug that in, and then I'll have an infinite series, and that infinite series may converge or it may diverge. So this is a function of x. When I plug in, let's say x equals 1, I get that 1/2 to the n series that we looked at before. So we'll have 1/2 to the first, plus 1/2 squared, plus 1/2 cubed, and so on. And if we started with a 1/2, we'd get 1. But then if you add the 1/2 to the 0 at the beginning, you get 2. But my point is, for a particular value of x, you've got a power series here. So here are a couple questions. Or you've got not just a power series, but you've got an infinite series that you're familiar with, one that you could test using those tests from the previous sections. So here are a couple questions. We might look at this and say, okay, I've got a power series. What does the series converge to? What does this series converge to? And when does it converge? Because I'm thinking of this now as a function of x. I'm thinking, okay, this is equal to f of x, some function. What x values can I put in so that this converges to a number? I know when I plug in x equals 1, this is 1/2 to the n, and we get 2. That's the sum of that series. But what other x values can I plug in? Can I plug in 0? Yeah, I can add infinitely many zeros together. That should work just fine. What other x values are legal? What can we do here? It turns out that this series does converge, and it converges to a function, a well-known function that will be very easy for us to figure out. But one way to see that is to expand this series, multiply out all the terms, or excuse me, expand out all the terms, and then see if it's a series that we're familiar with. So just to get a better sense of what's going on, let's substitute in n equals 0, n equals 1, n equals 2, n equals 3, and so on. And then eventually we'll have just n, the nth term over here. So when n equals 0, I get x over 2 to the 0. When n equals 1, I get x over 2 to the first. When n equals 2, I get x over 2 squared. When n equals 3, I get x over 2 cubed. And this is a series, so we're adding them. There's a sigma there. So if I simplify this, I get 1 plus x over 2 plus x squared over 4 plus x cubed over 8, and so on. That's x to the n over 2 to the n, and you just keep going. Well, that's definitely an infinite series. Now, the key to answering this question lies in recognizing this as a geometric infinite series. You might be saying, no, geometric series we only have a geometric series if we're multiplying by the same thing to get from term to term, if we've got that common ratio r. And I know it doesn't look like it, but we do have a common ratio r. X is just a number. For a particular value of x, this is just a series. This is just a regular infinite series like those we studied in the other sections. So if x was equal to 3, this would be 1 plus 3 halves plus 9 over 4 plus 27 over 8 plus eventually 3 to the n over 2 to the n, and we keep going. So if x is a number, it looks like we've got a geometric series here. Let's look at it. What do I multiply by to get from term to term? Well, to get from here to here, I multiply by x over 2. And to get from there to there, do I multiply by x over 2 again? Yes, x over 2 times x over 2 is x squared over 4. Yes, so that works. What do I do to get from there to there? Do I multiply by x over 2 again? Yes. And if I multiply by x over 2 n times, I'm going to get the x over 2 to the n, or x to the n over 2 to the n, same thing. So we have a common ratio. So this series does converge, or this is a geometric series, and we know that geometric series converge when the absolute value of r is less than 1. So that's actually for the second question. This is asking when does it converge, or for what interval of x values does it converge? But let's answer the first question first. What does it converge to? Well, in general, geometric series converge to a over 1 minus r. I'm going to write it a little differently. Whenever we're dealing with geometric power series, I'm going to call this a of x over 1 minus r of x. Now, a of x is not multiplication, that's a as a function of x. And r of x is not multiplication, that's r as a function of x. So this is a function of x, and that's a function of x. But this is the function of x that's the common ratio, and that's the function of x that's the first term of my series. So I look over here at my expanded series. What's my first term? It's just 1. And then in the denominator, I've got 1 minus r of x. And r is x over 2, because that's what we're multiplying by to get from term to term. Or you could just look in those parentheses. R is the number that's being raised to the nth power. So the number being raised to the nth power is the x over 2. Okay, so that's the sum of the series. Now, normally we don't like to have the complex fraction, so we'll multiply by whatever's necessary to get rid of that denominator. So just multiply by 2 over 2. So I get a 2 in the numerator, and then I distribute this 2. 2 times 1 is 2. X over 2 times 2 is x. So this infinite series converges, and it converges to 2 over 2 minus x. But not all of the time, only some of the time. So this is just another way to write this. That kind of blows my mind. It reminds me of that image that was floating around Facebook for a while. It was like a check somebody was paying their rent with, and it had a bunch of mathematical symbols on it. I guess they were annoyed, or just trying to be funny, I guess. But they had written out their rent in sigma notation. This is kind of the same thing. Like, this is another way to write this, but only sometimes, only when the absolute value of r is less than 1. So let's see when this converges to this. Well, this will converge, this infinite series will converge to this when the absolute value of r of x is less than 1. And remember, r of x is x over 2. That was what we were multiplying by to get from term to term. And then remember how absolute value inequalities work. If you have the absolute value of x is less than k, and k is a positive number, that means that x is between negative k and k. That's the only way that happens. So if this absolute value is less than 1, what that is telling us is that x over 2 is between negative 1 and 1. And if I want to get x by itself in the middle, I just multiply all 3 parts by 2, and I get this. I get a negative 2 on this side, an x in the middle, and a 2 on the right. So this infinite series actually converges to a function. But only on this condition, only when x is between negative 2 and 2. If x is equal to 2, we've got 1 to the n. So that's just 1 plus 1 plus 1 plus 1 plus 1. Infinitely many 1s added together, you know those partial sums are going to infinity. If it's negative 1, or excuse me, if x is negative 2, we get negative 1 to the n. So you get, well, negative 1 to the 0 is 1. It'll be 1 minus 1, 1 minus 1, 1 minus 1. So half the time, those partial sums are equal to 0, the other half the time the partial sums are equal to 1. So the partial sums, the sequence of partial sums diverges, and the series diverges. But if x is between -2 and 2, then this is a proper fraction, and I can take my proper fraction to the n, and we'll get a number. We'll get a number out of that, because it'll be a geometric series. It'll be a particular case of a geometric series, and it's going to converge to this. I think that's pretty cool. So let's say x is equal to negative, let's say negative, let's say -1. Well, the question might be, what does the series converge to? When x equals -1. Well, it's actually pretty easy. You just plug in -1 down here. So we get 2 over 2 minus a -1. So we get 2/3. So this is, we can think of this as a new function. F of -1 is 2/3, and that's the sum of -1/2 to the n, as n goes from 1 to, or 0 to infinity. Add all of those up. So you get 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16, and so on. You've got that alternating geometric series. Add all of those together and you get 2/3, turns out. So you say, well, what if x is 0? Well, if x is 0, according to this I get, well, 2 over 2 minus 0, 2 over 2, that's just 1. And actually, if I look at this expanded form of my series, that makes sense, because if x is 0, all of these guys are gone, and what are we left with? We're left with the first term. We just get a 1. So, yeah, this is just another representation for this function. And if I plug in any x value between here and here, any x value between -2 and 2, well, that's going to give me a geometric series. And that geometric series will converge to 2 over 2 minus that x value, whatever it was that you plugged in. So that's an example of a geometric power series. And again, how did I know? Because to get from term to term, I was always multiplying by the same thing. I was always multiplying by x over 2. Now, earlier we talked about the coefficients of the power series. Well, what are the coefficients? Well, the numbers that I'm multiplying x by are 1, 1/2, 1/4, 1/8, 1 over 2 to the n. Okay, so those are the coefficients of the power series. And the center of the series, that's whatever you're subtracting from the x's in the parentheses. Since we're not subtracting anything from these x's, this is a power series that's centered at x equals 0. Okay, so it's centered at 0. Now, we can think about this a little bit differently. Initially we said, okay, we've got a series, what does it converge to? And we recognized it as a a geometric series. And we said, it's geometric, therefore it converges to a over 1 minus r. And that was pretty cool. And after simplifying, we got this. And we said, yes, that's a great idea. It does converge to that, as long as x is between -2 and 2. Now let's think about what this means if we don't take the whole series. We just take parts of the series. So we're going to change our perspective a little bit. Instead of thinking, I've got an infinite series, what is it equal to? We're going to say, I've got a function. How can I rewrite that function? How can I express that function as powers of x, or as a sum of powers of x? And that's what this infinite series is telling us. The partial sums of this series are approximations to this function, as long as we stay near the center of the series. So let's look at a couple of partial sums of this. And since the partial sums are polynomials, we tend to use p with a subscript or t with a subscript later to represent those polynomials. That 0 means we're talking about the 0th degree polynomial approximation of this function. 0th degree just means constant. So we get 1 there. The first degree polynomial approximation of the function is just 1 plus 1/2 x. Just the first two terms. Second degree polynomial is going to be 1 plus 1/2 x plus x squared over 4, and so on. Third degree, we don't have that third degree term up there, but we know we multiply this one by x over 2 to get the next term because it's geometric, and we get that. So these are approximations to our function, and they're good approximations as long as we stay close to x equals 0. If you're saying to yourself, why do we have to stay close to x equals 0? I'll tell you in just a second. Now, before I graph this, before I graph these guys, and I'm just going to make a very rough sketch. I want to sketch this function over here. This is undefined when x equals 2, so it has a vertical asymptote. Looks like that. When x is 0, y is 1. When x is 1, what do we get? When x is 1, we've got 2 over 2 minus 1. 2 minus 1 is 1, so we get 2. Okay. When x is negative 1, what do we get? Well, 2 over 2 minus negative 1, that's 2/3. And as x goes to negative infinity, this is going to be a large positive number. 2 over a large positive number is a small positive number, so this has an asymptote like this. And as x approaches 2 from the left, so let's say that x is like 1.9. I've got 2 minus 1.9, that's 0.1, so this is a tiny positive number. 2 over a tiny positive number is going to be a large positive number. So that is the trend. That is a rough sketch of y equals 2 over 2 minus x. Now on the other side, when x equals 3, well, we get 2 divided by negative 1. So we get negative 2 over here. When x equals 4, what do we get? We get 2 divided by negative 2, so that's negative 1. And so on. And as x goes to positive infinity, the number in the denominator is approaching negative infinity. So if 2 over a large negative number, it's going to be a small negative number. So the y values on the graph are going to be small and negative. It'll look roughly like this. That's y equals 2 over 2 minus x. Now this series only converges to this function when x is between negative 2 and 2. So it only converges for this part of the graph here. This is equal to this, starting at negative 2 and then going to 2, but not equaling 2, obviously, because we would be dividing by 0. You might say to yourself, okay, well, what does this mean again? Well, let's check it out. Let's graph these. P sub 0 of x equals 1, that's a 0th degree polynomial. When x equals 0, these are all gone. That's what I get. So I just get a 1. So my 0th degree polynomial, or my constant polynomial, it agrees with our function at x equals 0. It agrees right there. But otherwise, they don't really have much in common. But notice what we get with this one. This is a line. If x equals 0, y equals 1, so it passes through that point. And then the slope is 1/2, so we go up 1 and over 2. Ooh, do you see it? You see that it's tangent to the graph at x equals 0? So this is a pretty decent approximation as long as I stay close to x equals 0. Now remember what we said, like these partial sums are approximations of the function near the center of the series. And this series is centered at x equals 0 because we're not subtracting anything from those x values. So this is an approximation. It's a pretty lousy approximation, but it's an approximation. It agrees with the function at 0. This is a linear approximation, or we could call it the tangent line. It has the same function value and the same slope as this function at 0. Now this one is a little bit harder for me to graph, but if we're close to 0, if we're very close to 0, let's say you keep going like this. The next term, the one that's missing, is that x cubed over 8. Now if x is very close to 0, x cubed is very small compared to x squared. So this might be a better approximation of the function, but leaving this off isn't leaving off much as long as we're close to 0, because something close to 0 raised to a larger power is going to be really, really close to 0 because we're taking a fraction and we're raising it to a power. So this guy is gone, basically. So this is a even better approximation than the last one was. It's a parabola approximating the function. I tried to draw this to scale, may or may not have worked out. Let's substitute in some values. When x is 0, we get 1. When x is 1, what do we get? I've got 1 plus 1/2 plus 1/4. 1/2 plus 1/4 is 3/4. So it's 1.75 when x equals 1. Damn, excuse my language. That's pretty good. Pretty good. And if x equals -1, what do we get? We have 1 minus 1/2. So that's 1/2. 1/2 plus 1/4. It's 1/2 plus 1/4. That's 3/4. I think our quadratic approximation looks like this. Well, and I don't really know what it looks like at x equals 2. What do we get? At x equals 2, that's a 1, that's a 1, and that's a 1. When x equals 2, we get 3. When x equals -2, what do we get? 1 minus 1, so that's gone, and then we just get a 1. Okay, so I've got this parabola, and I'm sorry that it doesn't look much like a parabola, but yeah, this is a parabola that's approximating the function here at x equals 0. The yellow function, the black function, and we're talking about that highlighted part of the function, that's being approximated by this horizontal line, which is a lousy approximation. This actual, like this line with the same slope, which is a better approximation. It's the tangent line. And then we've got a parabola that approximates the function, and it is a really good approximation for a large interval. And if we graphed this as well, we would see that this is an even better approximation to that. So these partial sums of the series can be thought of as approximations to this function over here. Now they're good approximations as long as we stay close to the center of the series, because if we're close to 0, 0 cubed is small. Like think about if x equals 0.01. If I take 0.01 and cube it, that's 1 over 100 cubed. How many zeros is that? 1, 2, 3, 4, 5, 6. That's a lot of zeros. That's 1 over a million. That's very, very small. And it's much smaller than 1 over 100 squared, which is right here. So we're saying this is approximately equal to this function because if we're close to 0, the next term is very small to the compared to the one before it. So we can almost ignore it, and when we ignore it, we'll say this is a very good approximation, but if I want a better approximation, take another term. And if I want a better approximation, take another term, and so on. So we've got these power series, and sometimes power series converge to functions, and then we can sort of turn it around and say, if I do have a function, let's use the partial sums of that power series to approximate the function. Now let's look at one more, one more series. And then we'll look at one more idea before we end this video. So let's say you're given this. The sum as n goes from 0 to infinity of negative 3x plus 3 all raised to the nth power. And you're asked to state the center of the series. So what is being subtracted or added to the x as you go from term to term. And we want to expand the series just to get a sense of what's going on. So expanding it is just showing the first few terms. 3 or 4 terms is fine. And then after that, maybe I might ask you, is this series geometric? And if it is geometric, find its sum. And the interval of convergence. Okay, let's see. Let's check it out. Well, when n equals 0, I get negative 3x plus 3 raised to the 0. When n equals 1, we get negative 3x plus 3 to the first. Then when n equals 2, we get negative 3x plus 3 squared. Then negative 3x plus 3 cubed. And you keep going indefinitely. Now the way this is written, it's not 100% clear what the center of the series is. One way that you can find the center of the series is you could take this expression that's in parentheses, this expression that's being raised to the nth, and you can set it equal to 0 and solve for x. That's one way. You could also factor this a little bit, and I think it's not obvious that that factors, but let's look at what's going on down here. I've got this to the 0, this to the first, this squared, this cubed. Well, does it factor? Well, I think it does. The negative 3x and the 3 have a 3 in common, obviously. Let's factor out the negative 3. So this is negative 3 times x would give me the first term, and negative 3 times negative 1 would give me the positive 3. And all of that's being raised to the 0. And that is the same as all of these. Inside of all of those parentheses, oops, that should be a 1. I can replace that expression inside by a negative 3 times x minus 1. And anything to the 0 is 1. And I've got a negative 3 times x minus 1 to the first, so that's negative 3 times x minus 1. And here I've got something times something squared, so I can square the first factor and square the second factor. And then I've got something times something cubed, so I can cube the first factor and cube the second factor. And we keep going. So this is the expanded form of that. Now it's a lot more obvious what the center of the series is. The center of the series is usually what you're adding or subtracting from the x inside the parentheses. But really what makes it the center is it's the value of x that you would substitute so that all the other terms disappear. If I replace x with 1, this is gone, and this is gone, and this is gone. So this is equal to 0 when x equals 1, so x equals 1 is the center of our series. Now, if you didn't factor it, or if you didn't think to factor it, it's not obvious that you would do that. So you might say to yourself, how else would I find the center, Miss Townsend? Well, you take this expression that involves x, set it equal to 0, and solve for x. So we'll subtract 3 from both sides, divide both sides by negative 3, and you get x equals 1. Okay, so this is we've stated the center is x equals 1. We expanded the series. After factoring, it looks like this, and then the question is it geometric? Well, what do I multiply 1 by to get this? Looks like negative 3 times x minus 1. if I multiply this expression by negative 3 times x minus 1, question is, do I get positive 9 times x minus 1 squared? Negative 3 times negative 3 is positive 9. X minus 1 times x minus 1 is x minus 1 squared, so we're good. So if I do it again, does that work? 9 times negative 3 is negative 27. X minus 1 squared times x minus 1 to the first is x minus 1 cubed. Yes. So this is geometric. And our common ratio is negative 3 times the quantity x minus 1. So the question says, state the center. We stated the center. Expand the series. We did. Is it geometric? Yes, because we're multiplying by the same thing to get from term to term. Also, you could say, if x is a number, I've got a number raised to the n there. If we've got a number raised to the n and there's just a number out front, just an implied 1, yeah, that's a geometric series for a particular value of x. So we want to find the sum of the series and the interval of convergence now. The sum of the series is the first term over 1 minus the common ratio. The first term is 1, and the common ratio is negative 3 times x minus 1. So if you distribute the negative, you get a positive 3. Distribute the 3, you get 3x minus 3. And the 1 plus the negative 3 is negative 2. So this series converges to 1 over 3x minus 2. Okay, that's nice. So this converges to this, but not all the time. It only converges to this when the absolute value of r is less than 1. So we'll say that converges to that when the absolute value of r, which is a function of x, is less than 1. And that means that r was this expression. Absolute value of r is absolute value of negative 3 times the quantity x minus 1, and that has to be less than 1. Now the absolute value of the negative 3 is just going to be a positive 3, so that can come out front. And then you'll divide both sides by 3, and then you'll see this. Now that expression in the absolute value bars, if that absolute value is less than 1/3, that means that expression inside has to be between negative 1/3 and positive 1/3. So we'll add 1 to all three parts. Negative 1/3 plus 1 is 2/3, and 1/3 plus 1 is 4/3. Okay, so that is the interval where the series converges. That's called the interval of convergence of the series. And we know that that's the interval of convergence because geometric series converge when the absolute value of r is less than 1 and diverge otherwise. So this is geometric, and it converges under this condition. Now I could draw this on a number line. Notice I've got this inequality. So I'm going from 2/3 to 4/3. That's my interval. Halfway in between 2/3 and 4/3 is a 1. That's no coincidence. 1 is the center of the series, and I also see the 1 in this absolute value. Whenever I see this absolute value of x minus a constant is less than a number, that's telling me that, well, that's telling me that this interval is centered at this number, so it's centered at 1, and then we're going to add and subtract this number from here. You're saying, why is that true? Well, let's look at this inequality. If this is equivalent to this, that tells me that x minus 1 is between negative 1/3 and 1. When I add 1 to all three parts, what do I get? I get 1 minus 1/3 and 1 plus 1/3. So I go 1 minus 1/3, we end up over there, and 1 plus 1/3, we end up over there. So our interval of convergence looks like this if we graph it. Normally we write it in interval notation this way. And the radius of convergence, that's defined to be half the size of this interval. So there are two ways you can find it. You can just draw a picture like this and you can see it. R is 1/3 because I am going from 1 to 4/3 here and 2/3 to 1 over there. Another way to find R is if you call this A and that B, R is B minus A over 2. So do the 4/3 minus 2/3 and then divide by 2 and you get 1/3. That's one way. Or you can look at it this way. If you see an inequality like this, I'm sorry, this is such a mess. We have the absolute value of x minus c is less than r. Now the number in front of the x has to be a 1, otherwise that's not going to be r over there. C is where your interval is centered and r is that radius. It's the number that you're adding and subtracting to c to get the rest of the interval. Or you could just do b minus a, so 4/3 minus 2/3 is 2/3, 2/3 divided by 2 is 1/3, and that will get you r as well. So you've got two ways of getting r. Using this formula and through pattern recognition, recognizing the c there and then the r there. Alright, so I just showed you two examples of geometric power series. And we also said that we could take the partial sums of those power series and use it to approximate the sum of the series. As long as you're near the center, it's a good approximation. But we were just talking about what's called the radius and interval of convergence of a power series. I'd like to show you what the general forms of those are for series. Now, remember the interval of convergence is just an interval of x values for which the series converges. It's like the domain. I think of it like a domain. It's saying if this is a function, f of x represents the sum as n goes from 0 to infinity of a sub n times x minus c to the n. If this is a function, what x values can I put in so that when I add them all together I get a y value out that makes sense? So this is similar to a domain. So I'm just going to say think domain because that's what I do. What x values work for this? Well, it turns out there are only a few possibilities. Either all of the x values work, so you might have the case where the interval of convergence is all real numbers, and then we would say that the radius of convergence is infinite. It really bothers me writing down r equals infinity, just a notation thing. So if I draw it on a number line, we're saying there's the interval of convergence. This series converges all the time from negative infinity to infinity. That's one possibility. Or the possibility is r is just a finite number like it was in the last two examples. In that case, you're going to have an interval. It will be centered at the center of your series. And then you're going to go to the center plus r and the center minus r. And those endpoints may or may not be included. So it might look like that, or that side might be colored in, or that side might be colored in, or they both may be colored in. So the interval is from c minus r to c plus r, or c minus r to c plus r inclusive, or this endpoint might be included and the other one's not, or both endpoints may be included. With the geometric series, we always had something like this because it only converged when the absolute value of little r of x, that common ratio, was less than 1. But for other series, we'll see you could have any of these behaviors, And then the last possibility is that your power series converges at C only. So the interval of convergence, it's a degenerate interval. It doesn't have much going on. It's just C. Just a single point. In that case, the radius is pretty small, so small that we call it 0. So we say r equals 0 here. Here r is a finite number, and there we write r equals infinity. You might be saying to yourself, well, that doesn't look that special. I think you covered all the cases. What this is saying is whenever you have a power series, it either converges at a point or on an interval or on the entire real line. This never happens. It doesn't converge for a while and then skip some x values and then converge for a little while longer. That's not a possibility at all. The possibilities are this: at a point, on an interval, or on the whole line. And the center is always included. This infinite series always converges at its center. Now, we talked about how to find the interval and radius of convergence if you have a geometric series in the last two examples. Here's our first example. We said this converges as long as the absolute value of r is less than 1. So if it's geometric, if you're multiplying by the same thing to get from term to term, you just identify r, set it to be less than 1, and then solve for x in the middle. That's a possibility. If it's not geometric, so we're dealing with a power series, and the power series is not geometric. Then you want to do something else. You want to use the ratio test. In the next video, we'll use the ratio test to find the intervals of convergence and the radii of convergence of several series. Yep. So I'll just save that for the next video. But that's your introduction to power series. So power series are like infinitely long polynomials. You look at it and it looks like this. It looks just like a polynomial. It just has little dots at the end that indicate that it goes on forever. The center of the series is that number that you're adding or subtracting from the x values. It's the value of x that would make all of these terms go to 0. So if x equals c, all of these guys would be gone. And that center is important because when we look at partial sums of a power series, like these guys, and we're using them to approximate the function, these partial sums are good approximations of the function as long as we stay near the center. So that's why we call it the center. Coefficients of this series are just the numbers out front of that x minus c. A sub 0, a sub 1, a sub 2, those represent numbers. For a particular series, they have values. This is 1, 1/2, 1/4, 1/8, 1 over 2 to the n. That's our coefficient. And a geometric power series is a power series that is geometric. To get from term to term, we always multiply by the same thing. Now, using the method in this video, you can find the interval and radius of convergence of a geometric power series. And then the last thing we talked about was the interval and radius of convergence. There it is, right here. You've got three possibilities. It either converges at the center, it converges in an interval around the center, or it converges on the entire real line. It's never it never does this thing where it converges for a while, skips some, and converges again somewhere else. Now, if the series is not geometric and we want to find the interval and radius of convergence, we're going to have to use the ratio test, and I'll save that for the next video.